Hello everyone, welcome to our presentation. We are Group 3 and this is our Project 1 for the course ENG3002 Engineering Mathematics 2. This project is supervised by our lecturer Dr. Mahfuza and our group members are 5 people including me, WAFAA, HARITH, NUSRAT and AFRINA. In this presentation, we will be exploring 5 different case studies that are related to the differential equation. Each case study shows how differential equations are used to model and solve real-world engineering problems. We hope this video helps you understand the concept and importance of differential equation better. So let's begin our presentation. So today I will be talking about my case study 1, which is about spring motion, or in other words, how a spring moves when a force is applied to it. This motion follows Hooke's law, which states the force of the spring is directly proportional to how much it is stretched or compressed. The formula is F equals to negative kx, where F is a force, k is the spring constant, and x is the displacement. Now, when we study how the spring moves with time, we use a differential equation. The equation is m bracket delta square x over delta t square plus kx equals to 0. Here, m represents the mass attached to the spring. Delta square x over delta t square is the acceleration, and then kx is the restoring force pulling it back. Now let's look at its classification. First, it is an ordinary differential equation ODE because it involves derivatives with respect to a single independent variable, which is time t. It is second order equation since the highest derivative in the equation is the second derivative, where delta square x over delta t square. Third, it is linear equation because all of terms involving dependent variable x and its derivatives appear to the first power and there is no product of variable or derivative. Finally, it is homogeneous also because there is no external force or constant term added to the equation, where the right hand side is still 0. So, overall, this is a second order linear homogeneous ordinary differential equation that represents simple harmonic motion of spring mass system. Thank you.
Assalamualaikum and good evening. My name is Puteri Wafa NAJWA binti JAMIL and my matrix number is 231033. Now let's go through to my topic, where it is about the equation for electromagnetic wave. So this is derived equation from Maxwell, where delta square E over delta t square equal to c square times delta square E over dx square. As you can see from here, E is represent the electric field, where the dependent variable describing the oscillating field. T represent time, is the independent variable representing the temporary change, while x is the spatial variable along x-axis, and lastly is the speed of wave. It is constant relating the spatial and temporary derivative. Next, I would like to talk about the classification, where it consists of 4 classifications. The first one is a partial differential equation. As you can see from here, it's been highlighted where t and x are different variable and it's at the independent. So this one is we consider it as partial differential equation. Next is second classification, where second order differential equation, also from the same equation, where it have power after the delta or maybe after the variable. So this represent a second order differential equation because of the square. Next is the linear differential equation, same equation, but linear is supposed to be, or it will show that E and its derivative are never square. And lastly is the homogeneous differential equation, where from this equation we should not or should never show the extra variable at the end. Let's say after the c square plus delta square E over dx square, plus maybe like plus b, so b are not supposed to be added at the back, or it will call as non-homogeneous. So that is all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Harith bin MOKHTAR and my matric number is 22347. Today we present case study 3, which is the equation of RC circuit. The circuit is dV over dt plus 1 over RC multiplied by V equals to 0. V is equal to voltage across the capacitor, R is resistance, the C is the capacitor in the circuit, and T for time. Classification of the equation. So for this slide, we are looking for the classification of the differential equation that represent the RC circuit discharge. Now let's classify this equation step by step. Ordinary differential equation, ODE. It's called an ordinary differential equation because it has only one independent variable, which is time. That means the voltage changes only with respect to time. The second is first order differential equation. It's a first order equation because the highest derivative that's appears is dV over dt, which is the first derivative of voltage. The third is linear differential equation. Next is a linear differential equation because it has derivative appears to the first power. There's no power, no product, and no linear function. Lastly, it's a homogeneous equation because it doesn't have any external input or constant term. The right hand side is equal to 0, meaning there's no external voltage source driving the circuit. That's all from me. Thank you.
The next case study is about unsteady state heat transfer. So the equation is describe how temperature inside a cylinder like a sausage or canned food change with time and position is a radius due to the heat conduction. It's come from applying the Fourier's law of heat conduction and energy conservation to a small cylinder element of the foods. So the equation is the partial derivative of temperature with respect to times equal with alpha multiply in the bracket the second partial derivative of temperature with respect to the radius squared plus 1 over radius time the first partial derivative of temperature with respect to radius. So T is the temperature, R is radius, small capital of T is time, and alpha is the thermal diffusivity. So next is about the type of calculation in this equation. The equation is partial differential equation PDE because it depends on which two independent variable is a radius and the time. The order is the second order because the second derivative with respect to R. So the equation also linear because the temperature and its derivative appear to the first power. And the equation also homogeneous because when no internal heat source term, right hand side become to equals 0.
Assalamu alaikum everyone. This is NUSRAT JAHAN AISHY, matric nom 217573. Today I will be presenting my project on modeling radioactive decay using differential equations. So basically, radioactive decay is a process where unstable atomic nuclei lose energy by emitting radiation over time. We can describe this behavior mathematically using an ordinary differential equation, or ODE, that models how the number of undecayed atoms decrease continuously. So the main equation for reductive decay is Tn by dt equal to minus lambda n, where n is the number of undecayed atoms, t is time, and lambda is decay constant, representing the probability that an atom decays per unit time. This equation shows that the rate of decay is directly proportional to the number of remaining atoms. By solving this equation analytically, we get n t equal to this equation, which represents an exponential decay. The number of atoms decreases rapidly at first, then slows down as time increases. The equation can be classified as follows. Ordinary differential equation, ODE. It depends on one independent variable, which is time. First order, only the first derivative, dn by dt appears. Linear, n and its derivative appears to the first power. Homogeneous, there is no external or source term. RHS is equal to 0. It means the right hand side is 0. So, in conclusion, reductive decay follows a simple first order linear homogeneous ODE that perfectly models how unstable nuclei change over time. This concept is fundamental in nuclear engineering, medical imaging, and environmental studies, showing how mathematics directly connects to real engineering applications.